Good afternoon, everyone. Let's start our section. So the first speaker, paper is, the title is Learning Models of Vision Head Manipulation, will present by Berk Calli. So welcome the speaker.
So thank you very much for the introduction. So in our lab, we mainly focus on making manipulation and grasping tasks easier by relying on passive adaptation of our gripper design. We achieve this by simply designing some underactuated grippers that can adapt to the shape of the hands, even very complicated shapes. And they also allow intentional or unintentional contact with the environment. Like, long story short, what we do here is trying to make the manipulation task easier, but also make it possible for very simple systems with minimal control effort, minimal sensor requirements, and minimal planning. And for this purpose, we have designed various underactuated hands, and some of which you can see here. These are open source hands. They are very inexpensive, by the way, compared to their fully actuated counterparts, and they are very easy to fabricate. So you can actually go to our website and download these models and fabricate it yourself. And also, these hands provides us the compliance and adaptability that we are seeking for a successful manipulation operation. And in literature, we see other underactuated hands too. And actually, these hands has been tested for their grasping performance quite thoroughly, I must say. And the manipulation community at large agrees that compliant hands are very, very effective when it comes to grasping. But how about after grasping? So this is what we are considering. And when we want to manipulate an object after we grasp it within hand, there are some challenges, but there are also a lot of perks coming with it. For example, as humans, we are heavily relying on within hand manipulation skills. Almost all the manipulation actions that we have also includes a within hand manipulation action. So if we include such abilities in a robotic system, we can enable more human-like manipulation actions. And also, this also means that we allow fine positioning of the object in hand's workspace with lower inertia fingers rather than whole arm motions. This means that we have lower energy requirements, but together with that, we have a potential of more precisely moving an object within the workspace. Also, thanks to the added degrees of freedom coming from the gripper, we extend the workspace of the gripper, which allows us to avoid some obstacles and other types of manipulation constraints. And also, since we can change the pose of the object within hand, we avoid unnecessary regrasping actions, which makes the manipulation operation much more efficient. So in order to have all these advantages, we need to conduct a manipulation control. But conventional ways of doing this actually requires accurate hand object models. For example, we need the very accurate model of the object. We require contact locations to be known both on the object and on the finger. And we need to know friction coefficients between the object and the gripper. And we also need to have a very accurate hand model. But apart from these, we also need to track the state of the hand object system all the time, which brings additional sensory requirements such as joint sensing and force sensing. When we look at this picture, we see that many of these parameters are not available to us very easily. For example, if we are operating in unstructured environments, we don't have object models available to us. Contact locations are very hard to estimate. Friction coefficients is definitely very hard to obtain. And depending on the hand, we may have some sensor modalities, and we may not have them in some other gripper designs. However, underactuation again saves the day here. So underactuation provides stable closed chain with the object, and we have it almost for free. So we don't use here joint sensing, we don't use here force sensing. but we still have stable contact. In order to have such a close-up chain with fully actuated grippers, we need to define and meet some additional constraints, which is a much more difficult work. But in underactuated hands, we get it with very easily with minimal amount of planning. And this is actually achieving such a closed chain and maintaining it during a within-hand manipulation operation is the key. Once we have that, in our previous work, we have seen that we can very precisely move the object within the gripper's workspace using very simple vision feedback. Here we are also using very, very simple hand object models, not accurate at all. They are almost like a binary Jacobian that we are using here. And again, we are not relying on force sensors or joint encoders. And however, when we manipulate an object, during this operation, we see that a lot of manipulation phenomena is happening. For example, the object can roll within the surface of the fingers. It can, but at times, it can go out of the workspace of the hand object system and can drop. It might slide on the finger surfaces, or it might get stuck on at gripper at the hand object system singularities. By the way, we are calling the rolling operation normal operation too, because it is happening more frequently. But in a manipulation operation, this kind of transition between these modes are happening all the time, and it's very important to recognize when these transitions are happening. Because we want to either trigger these modes or prevent these modes, depending on our application. For example, if we want to precisely position our object within hand, we want to avoid dropping it. But if we want to release an object, we want to trigger the drop mode. Similarly, for example, for sliding, sometimes we want to trigger sliding because we want to position the object in a particular way within hand. But also, sometimes we want to avoid it because simply we want to have a tighter grip on the object. So recognizing the transitions between these modes are quite crucial in order to conduct reliable in-hand manipulation. And we achieve this in this paper with total model-free, data-driven way. And we are not relying on object models or hand models. Here you can see that we are following the same philosophy that we were having for grasping with underactuated hands and vision-based control with underactuated hands, right? So we are not relying on sophisticated sensing. We are not relying on accurate knowledge of hand object models. When we look at the related work, we see that there are papers that detect sliding mode, and also there are some papers that detect grasp stability and can detect whether the object is within the vicinity of dropping or not. But these works heavily rely on force sensing at the finger locations, at the contact locations, and they also they are only recognizing particular modes. In our case, we are recognizing all these four modes at once and the transitions between them. Our methodology is the following. So we use supervised learning techniques. We utilize visual features and actuator features. You can see the full list of our features here. And our actuator features here are actuator positions, actuator velocities, and actuator loads. And, but it is very important here to notice that these are not coming from the joint locations, but they are actually coming right at the base of the gripper, because the actuators are located over there. And these actuators are basically pulling the tendons in order to operate this underactuated system. And also, we are using visual features like that we obtain from markers that we are located at the fingers and on the object, and we use link positions, velocities, and orientations together with object positions and velocities. We also use commands, which can be the output of the controller or a manual command given by the user. This is basically where we want the object to go. Using this feature set, we collect training data with video streams, as you can see here. So this is a video stream example for the drop case. And we label the instances when the transition between modes are happening. And we did this for 6 objects with different shapes and sizes, as you can see here. And we collected 1,050 observations. So we tested many classifiers. The top 3 you can see here. Extra trees provided us the best recognition rate of 69%. So this is a very, very high recognition rate for detecting all these 4 modes at once. And we also check the performance with a subset of these features for different scenarios. For example, if you don't have access to visual data and only using actuator features, we still have 93% success rate. Moreover, if we go and use only visual features but not actuator features, we still have 93% success rate again. So these are, again, very high recognition rates. We also tested the extrapolation ability of our classifier and trained our classifier with small and medium objects and test its performance on the large objects and see that we achieve more than 92% success rate in this case, even with the sub-features that I was just talking about. And this is, again, this gives us a good indication of how robust our scheme is. Also, our classifier is fast enough to be integrated in real-time loop. And here you can see that the object, when it gets stuck in a singularity, it is reliably detected by the classifier. When it is about to drop, this is again detected by the classifier, and the system is blocked from going this particular direction. But it can go to other directions, and sliding can also be recognized very reliably. And this generalizes for different object shapes, as you can see here. Again, like the system is stopped from going a particular direction. But one interesting thing happening here is that sometimes the classifier gets confused between sliding mode and the rolling mode. And it will happen right around this time. Because actually, with such a motion of the gripper, if we would have flat surfaces, this object would slide. But since we have no information about the object geometry here, the classifier, it's very challenging for classifier to detect such subtle changes, and it sometimes gets confused between sliding and rolling. And thank you very much for your attention, and if you have questions, I'm happy to answer.
So, any questions from the audience? Okay, I may have 1 or 2. So what about the diffraction between the object and the finger may affect the algorithm you proposed?
The interaction between
yes.
Object and the finger? Yeah, basically, so that interaction basically is given, that contact is basically maintained almost automatically with our underactuated design. And basically, we are not modeling those kind of interactions, and we are only using a data-driven way. Because actually, in reality, it is very hard to model this kind of contact interactions. So that's why we want to rely on this kind of data-driven approach. And also, this goes hand-to-hand with our previous approaches, which requires minimal amount of modeling and sensing.
Well, is any other question from the audience?
Yeah.
Okay.
Hey, Berk, it's Tucker.
So it's the second speaker. Can you test your laptop now? The second speaker.
So in your work, you have a fixed wrist pose. So how do you think this would scale if you're changing the orientation with respect to gravity, for example?
Yeah, sure. This is actually like a direction that we want to follow. We want to extend our training set with more challenging cases, and also we want to actually extend this to a 3D case that we can manipulate the object in 3D. because now it is only planar. So, but this is, I think, a very promising direction to go, which would allow us to use minimal amount of modeling. But also, another thing, by the way, that we are aiming to do is detect features that would be invariant to any gripper. And we are now searching for these kind of features, like contact location curvatures, etc., that could be detected through visual means. Thank you very much, Tucker.
I think due to the time constraint, you may communicate after the section. So thanks the speaker again. Okay.